Hello everyone. So in today's video, we are going to go over this paper titled SSMBA Self-Supervised Manifold-Based Data Augmentation for Improving Out-of-Domain Robustness by Nathan Ng, Kyung-Hyun Cho and Mazze Vasemi from University of Toronto and New York University. Alright, so let's jump into the abstract. Models that perform well on the training domain often fail to generalize to out-of-domain examples. Data augmentation is a common method used to prevent overfitting and improve out-of-domain generalization. So by out-of-domain, this includes things like words which were not present in the training sample. So the words which it failed to see in its training duration. However, in natural language, it is difficult to generate new examples that stay on the underlying data manifold. We introduce SSMBA, a data augmentation method for generating synthetic training examples by using a pair of corruption and reconstruction functions to move randomly on a data manifold. We investigate the use of SSMBA in the natural language domain, leveraging the manifold assumption to reconstruct corrupted text with masked language models. In experiments on robustness benchmarks across 3 tasks and 9 datasets, SSMBA consistently outperforms existing data augmentation methods and baseline models on both in-domain and out-of-domain data, achieving gains of 0.8% on out-of-domain Amazon reviews, 1.8% accuracy on out-of-domain MNLI, 1.4 blue on in-domain IWSLT 14 German to English dataset. Alright, so basically what they do, what I get from the abstract is for the training data, they're trying to corrupt some words randomly using a corruption function and then using a reconstruction function to reconstruct them. And essentially what the reconstructing is using that corrupted sentence, the words which were corrupted are now being filled in by a language model. So this generates new examples. Okay, so the introduction. Training distributions often do not cover all of the test distributions we would like a supervised classifier or model to perform well on. Often this is caused by biased dataset collection or test distribution drift over time. Therefore, a key challenge in training machine learning models in these settings is to ensure they are robust to unseen examples. Since it is impossible to generalize to the entire distribution, methods often focus on the adjacent goal of out-of-domain robustness. Data augmentation is a common technique used to improve out-of-domain robustness by synthetically generating new examples, often by perturbing existing examples in the input space. If data concentrates on a low-dimensional manifold, then these synthetic examples should lie in a manifold neighborhood of the original examples. So, from how I think about this, if you have a vector space and your sentences have a word embedding or a vector space representation, then these synthetic examples which are generated from them would also be in their vicinity. So the cosine similarity on or any other metric which you would like to uh, measure distance by would be lower compared to two other samples which were not generated in the same fashion. Alright. So training models to be robust to such local perturbations has been shown to be effective in improving performance and generalization in semi-supervised and self-supervised settings. When the underlying data manifold exhibits easy to characterize properties as in natural images, simple transformations such as translation and rotation can quickly generate local training examples. So in images, if you flip an image or you zoom in an image and do things of this sort, it is a new image with a similar label, but for natural language you cannot do this simply. However, in domains such as natural language, it is much more difficult to find a set of invariances that preserves meanings or semantics. So in this paper, we propose self-supervised manifold-based data augmentation (SSMBA), a data augmentation method for generating synthetic examples in domains where the data manifold is difficult to heuristically characterize. Motivated by the use of denoising autoencoders as generative models, we use a corruption function to stochastically perturb examples of the data manifold, then use a reconstruction function to project them back on. So if you have a manifold and you have a sample X, then the corruption function pushes it off the manifold and the reconstruction function ideally brings it back to the manifold M. This ensures new examples lie within the manifold neighborhood of the original example. SSMBA is applicable to any supervised task, requires no task-specific knowledge, and does not rely on class or data set-specific fine-tuning. You've seen that this is just a general approach of corrupting and reconstructing examples. We investigate the use of SSMBA in the natural language domain on three diverse tasks, spanning both classification and sequence modeling, sentiment analysis, natural language inference, and machine translation. In experiments across 9 datasets and 4 model types, we show SSMBA consistently outperforms baseline models and other data augmentation methods on both in-domain and out-of-domain data. So I guess the idea for what SSMBA is doing is pretty clear now. So let's just have quickly cover these sections to see what they're actually doing. Alright, so background and related work. So for data augmentation in NLP, the problem of domain adaptation and out-of-domain robustness is well established in NLP. Existing work on improving generalization has focused on data augmentation, where synthetically generated training examples are used to augment an existing dataset. It is hypothesized that these examples induce robustness to local perturbations, which has been shown to be effective in semi-supervised and self-supervised settings. So essentially, you're giving it more examples to learn on, so more points to train on. So the model is bound to learn more new things. And since the synthetically generated examples are variations of the initial example, and mostly the differences are not too large, because then you'll be risking losing the task specific nature or the label of the sentence. So then perturbations are relatively minor in things like EDA. So in those cases, in suppose a vector space representation, those two sentences would still remain fairly close. Alright. So existing task-specific methods and word-level methods are based on human-designed heuristics. Back translation from or through another language has been applied in the context of machine translation, question answering, and consistency training. More recently, work has used word embeddings and LSTM language models to perform word replacement. Other methods focus on fine-tuning contextual language models or large generative models to generate synthetic examples. So I guess you know what back translation is. In back translation, what you do is you take a sentence, you convert it into some other language, say from English to Spanish, then you convert that Spanish sentence back to English. So what you're hoping for ideally is that the context remains the same, but the words being used in the sentence would be reordered, or new synonyms might be introduced in this translation process, which would essentially give you a new sentence with with the same label. For these LSTM language models, essentially what you're doing for is looking for replacement for words to generate new examples. So language model is, I guess, in some way, uh, either you mask off some words and ask the language model to predict it, or you ask for words. Yeah, that would be it, I guess. You mask off words and ask the language model to predict it. But to be sure, I'll have to go through these works as well. And the final is you will give the entire dataset to a generative model and fine tune it on that particular domain, and then ask the generative model to generate more information about that, or more examples with some random initialization. Alright, so VRM and manifold assumption. Vicinal risk minimization (VRM) formalizes data augmentation as enlarging the training set support by drawing samples from the vicinity of existing training samples. Typically, the vicinity of a training sample is defined using dataset depending heuristics. For example, in computer vision, examples are generated using scale augmentation, color augmentation, and translation and rotation. The manifold assumption states that high-dimensional data concentrates around a low-dimensional manifold. This assumption allows us to define the vicinity of a training example as its manifold neighborhood. The portion of the neighborhood that lies on the data manifold. Okay, sorry, this is just one sentence. So manifold neighborhood is the portion of the neighborhood that lies on the data manifold, and what they're basically saying is that for uh, the underlying assumption is this manifold assumption that the high dimensional data concentrates around a low dimensional manifold, And in vision you have all these techniques which are being used, which are essentially leveraging this vicinal risk minimization. Recent methods have used the manifold assumption to improve robustness by moving examples towards a decision boundary, generating adversarial examples, interpolating between pair of examples, or finding affine transforms. So these are just techniques. I'm not familiar with this particular technique, but generating adversarial examples is basically looking for examples where the model would fail. Interpolating between pair of examples is like using multiple examples to generate new examples, and finding affine transforms, for as far as I know, refers to getting some transformations which would create new examples. But to be sure, I'll again have to go through these works, which I plan to in some future videos. So sampling from denoising autoencoders. A denoising autoencoder is an autoencoder trained to reconstruct a clean input x from a stochastically corrected 1 x bar x prime, which is basically output of some model, which is basically uh, generated by learning a conditional distribution, which is this p of theta. We can sample from a denoising autoencoder by successfully corrupting and reconstructing an input using the following pseudo Gibbs Markov chain. So you're using a corrupted input, you're generating a corrupted input, and then you're using it to regenerate the original input. As the number of training examples increases, the asymptotic distribution of the generated samples approximates the true data generating distribution. This corruption reconstruction process allows for sampling directly along the manifold that p of x concentrates on, and p of x is basically the distribution of the data. Alright. So now masked language models. Recent advances in unsupervised representation learning for natural language have relied on pre-training models on a masked language modeling objective. In the MLM objective, a percentage of the input tokens are randomly corrupted, and the model is asked to reconstruct the original token given its left and right context in the corrupted sentence. We use masked language models as denoising autoencoders to sample from the underlying natural language distribution by corrupting and reconstructing inputs. So for a training set, you corrupt the examples, then you use the reconstruction function to reconstruct examples, and now you have the augmented data set, which is basically uh, your training set plus your so now your total set would be your training set plus your augmented data set. Alright, so let's have a look at the algorithm. So the function perturbation function is Q, reconstruction function is R. You have M samples. You train a model on F on D. So for given pair in the original data set, you do a random perturbation, then you reconstruct it, and you generate a new sentence, which is basically what you've done is you've generated a new sample, then you're using the trained model to generate a new label, or you preserve the original label, and then you basically this is your end of loop. So you have two nested loops. For each data point, you're going to do this thing where you uh, do perform this exact experiment n times, which is the number of augmented examples you want per sample, where you corrupt it, reconstruct it, and predict the label. Now you have an augmented data set, and then your total data set is the union of both the data sets. We now describe self-supervised manifold-based data augmentation. Let our original dataset D consist of pairs. Okay, we assume the input points concentrate around an underlying lower dimensional data manifold. Let Q be a corruption function from which we can draw a sample such that X bar no longer lies on the manifold. Let R be the reconstruction function such that X hat lies on the manifold. To generate an augmented dataset for each pair, you generate a perturbed example, then you reconstruct it, and a corresponding vector y hat can be generated by either preserving, or since if the sample is quite close to the decision boundary, maybe the one word which was uh, making it associate to a particular class is changed, then you need to repredict your label. So you need to repredict the label in more sensitive tasks. So for this, you can use a model which was trained on the original data. This operation can be repeated to generate multiple augmented examples for each input example. These new examples form a dataset that we can augment the original training set with. We can then train an augmented model on the new augmented dataset. In this paper, we investigate SSMBA's use on natural language tasks using the MLM training corruption function as a corruption function Q, so which is basically a mass language modeling corruption function, and a pre-trained BERT model as a reconstruction model R. Different from other data augmentation techniques, SSMBA does not rely on task-specific knowledge, requires no data-specific fine-tuning, dataset specific fine-tuning, and is applicable to any supervised natural language task. SSMBA requires only a pair of functions to generate data. So they mentioned the datasets they're using and the statistics. So the sentiment review Amazon dataset is a pretty standard dataset. So following Hendricks et al. 2020, they formed two datasets, which is the full dataset, which contains reviews from 10 largest categories, and the clothing dataset, which has the clothing category separated into subcategories by metadata. Since the reviews in Amazon review clothing come from the same top level category, the amount of domain shift is much less than that of AR full models. Uh, from that of the entire dataset. Models predict the review's 1 to 5 star rating. So basically, given a review, you need to predict the rating. SSD2 contains movie review excerpts. Following this is your Stanford tree bank or something dataset. Following Hendrick et al. 2020, we pair this dataset with the IMDb dataset, which contains full-length movie reviews. We call this pair the movies dataset. Model predicts a movie's binary review, so it produces a binary output which is either a positive or a negative sentiment. The Yelp review dataset contains restaurant reviews with associated business metadata, which we pre-process using Hendricks et al. 2020 model, and they predict again a 1 to 5 star review. So this is the dataset statistics. You have the number of domains, the average input length, the training size, and the testing size. For natural language inference, you have MNLI, which is a corpus of NLI data from 10 distinct genres of written and spoken English. We train on the 5 genres with training data and test on all 10. Since the dataset does not include labeled test data, we use the validation set as our test set and sample 2000 examples from each training set for validation. And ANLI is a corpus of NLI data designed adversarially by humans, such that state-of-the-art models fail to classify them correctly. The dataset consists of 3 different levels of difficulty, which we treat as separate textual domains. All right. So you have level 1, level 2, level 3. For machine translation, they're using the German to English and German to Romansh datasets. Romansh is a low resource language with an estimated 40,000 native speakers, where out of domain robustness is of practical relevance. Right. In the D to EN direction, they use IWSLT 14, which is a widely used benchmark to test in-domain performance. We use the Opus dataset to test out-of-domain generalization. We train on highly specific in-domain and disparate out-of-domain uh, texts also. Since domains share very little similarities in language, generalization to out-of-domain text is extremely difficult. In the DE to RM direction, we use a training set consisting of the Allegra corpus and Swiss press releases. We use blog posts from Convivenza as a test domain. Alright, so basically they've just described all of their data sets and how are they creating them or in what form are they using them. So for a model setup for sentiment analysis tasks, they use LSTMs and convolutional nets. For NLI tasks, they investigate fine-tuned Robota-based models, which are pre-trained bidirectional transformers. On both tasks, representation from the encoder are fed into a feed-forward neural net for classification. For machine translation tasks, we train transformers. For all models, word embeddings are initialized randomly and trained end-to-end with the model. We do not initialize with pre-trained word embeddings to maintain consistency across all models and tasks. Model hyperparameters are tuned to maximize performance on in-domain validation data. Training details and hyperparameters are there in appendix. So for the setting for all experiments, we use the MLM corruption function as our corruption function. We fine tune the total percentage of tokens corrupted, leaving the percentage of specific corruption operations. So 80% are masked, 10% are random, and 10% are unmasked. The same, alright. For sentiment analysis, the NLI experiments, we use a pre-trained Roberta-based model as a reconstruction R, and for translation experiments, we use a pre-trained German BERT model. For each input example, we generate 5 augmented examples using unrestricted sampling. For translation experiments, target site translations are generated with beam search with width 5. SSMBA hyperparameters include augmented example labeling methods and corruption percentages are shown based on in-domain validation performance. Alright, hyperparameters for each are again in Appendix D. Alright. So they've just described what is the corruption function, what is their reconstruction function, and the hyperparameters are present in the appendix. For the baselines on sentiment analysis and inline tasks, we compare against three data augmentation techniques. EDA is where you have random synonym replacement, insert, swap, and deletions. Conditional BERT contextual augmentation, CBERT, which fine-tunes a class conditional BERT model and uses it to generate sentences in a process similar to their own process. Unsupervised data augmentation translates data to and from a pivot language to generate paraphrases. We adapt UDA for supervised classification tasks by training directly on the back translated data. So on translation tasks, we compare only against methods which do not require additional training side monolingual data. Word dropout randomly chooses words in the source sentence to set to 0 embeddings. Reward augmented maximum likelihood RAML samples noisy target sentences based on an exponential of their Hamming distance from the original sentence. Switch out applies a noise function similar to RAML to both the source and target side, and they use the publicly available implementation. So these are the models which are they are comparing with. Right. Also, they are only comparing against methods which do not require additional target side monolingual data. What this basically means is the new data which they are going to generate the augmented data set is only going to require the original training set and does not use like general English information which some other data augmentation technique might be using. Alright. So for evaluation method, we train LSTM and CNN models with 10 random seeds, Roberta model with 5 random seed, and Transformer model with 3 random seeds. Models are trained separately on each domain, then evaluated on all domains, and performance is averaged across seeds and test domains. We report the average in-domain and out-of-domain performance. On sentiment analysis and NLI tasks, we report accuracy, and on translation, we report uncased tokenized blue for IWSLT and cased detokenized blue for with sacred blue for all others. Statistical testing are there in Appendix E. So let's have a look at the results. So these are the results. So in all of them, almost SSMB is outperforming except for movie reviews, where on the in-domain portion, the Seabot model beats it by a very slight, okay, not a very slight, almost 1.5% margin. Okay, seems interesting, but still it's really outperforming everything else out here. For MNLI and ANLI, it's quite amusing to see that on the out-of-domain performance, even without any augmentation, you get the same results. For Opus, you see with no augmentation does better than the SSMB or any other corruption model on the in-domain work. For your IWSLT works, you can see that again the SSMB model is outperforming. Alright, so let's read this up. Alright, on in-domain data, SSMBA outperforms baseline models and other data augmentation methods on all datasets, and 3x4 data and 3 out of 4 datasets for RNN models on average. SSMBA improves OOD performance by 1.1% for RNN and 0.7 for CNN, and in-domain performance by 0.8% for RNN and 0.4 for CNN. Other methods achieve much smaller out-of-domain generalization gains and perform worse than baseline models on multiple datasets. On the Amazon review, full datasets RNN trained with SSMBA demonstrate improvements in out-of-domain accuracy of 1.1% over baseline. On the Amazon review clothing dataset, which exhibits less domain shift than the full dataset, RNNs trained with SSMBA exhibit slightly lower out-of-domain improvement. CNN model exhibit about the same boost in out-of-domain accuracy across both the datasets. On the movie dataset, we observe a large difference in average sentence length between the two domains. SSMB still manages to present considerable gain in out-of-domain performance. Although RNNs trained with SSMB failed to improve ID performance, their out-of-domain performance in this setting still beats other data augmentation methods. On the Yelp dataset, we observe large performance gain on both the domains. For RNN, the improvement on CNN are more modest, but notably our method is the only one that improves out-of-domain generalization. Okay. So far it seems that the model is working as intended. Of course, it wouldn't have been a paper if it didn't, but the technique does not require any specific information and is able to perform well on so many different tasks. So for NLI, models trained with SSMB outperform on or match baseline models and data augmentation methods on both the data. Even with a more difficult task and stronger baseline, SSMB still confers large accuracy gains. Alright. All the other baseline methods hurt both in-domain and out-of-domain accuracy or confer negligible improvements. On the intentionally difficult ANLI, which is adversarially generated by humans, SSMB maintains baseline OOD accuracy while conferring a large 6% improvement on in-domain data. Other augmentation methods improve in-domain accuracy by a much smaller margin while degrading out-of-domain accuracy. So for ANLI, you can see you've got almost a 6% jump, while the out-of-domain accuracy has fallen from what no augmentation would have done. Surprisingly, pseudo-labeling augmented examples in the R2 and R3 domain produced the best results even when the labeling model had poor in-domain performance. So what this is referring to is basically this fact where you had three different uh, levels where with different difficulties. For machine translation, we compare our results with convolutional models and strong baseline transformers and dynamic convolutional models. SSMB improves blue by almost 1.5 points, outperforming all other baselines and comparison models. Compared to SSMB, our augmentation method offers much smaller improvements or even degrade performance. Table 5 shows these results for Opus and on DE to RM side. On Opus, where the training data contains highly specialized language and differs significantly both from other domains and the learned MLM Manifold, SSMB offers a small boost in out-of-domain blue but degrades in-domain performance. All other augmentation methods degrade both the performance, so it's still better. On DE2RM, SSMB improves out-of-domain blue by a large margin of 2.4 points and in-domain blue by zero point 0.4 points. Other augmentation methods offer much smaller out-of-domain improvement while degrading in-domain performance. Okay, for the analysis and discussion, in this section we analyze factors that influence SSMB's performance due to its relatively small size, number of out-of-domains, and amount of domain shift. We focus on analysis of the baby domain within the AR clothing dataset. Ablations are performed in a single domain rather than all domains, so error bars correspond to variance in models trained with different seeds, and results are not comparable with those in Table 2. Unless otherwise stated, we train CNN models and augment with SSMBA, corrupting 45% of tokens, performing unrestricted sampling when reconstructing, and using self-supervised soft labeling, generating 5 synthetic examples for each training exam. So they've now just analyzed their results and mentioned what is helping out and what isn't. So for the training set size, we first investigate how the size of the initial dataset affects SSMBA effectiveness. Since a small dataset covers less of the training distribution, we might expect the data generated by SSMBA to explore less of the data manifold and reduce its effectiveness. So we subsample 25% of the original dataset to form a new set, then repeat this process successively to form exponentially smaller and smaller datasets. The smallest dataset contains only 24 examples. For each dataset, we train 10 models on average performance, tuning a set of SSMB hyperparameters on the same ID validation data. Figure 4 shows the SSMB offers out-of-domain performance gains across almost all dataset sizes, even in low resource settings. Right, so you can see the SSMBA curve is continuously above the no augmentation curve. Right. So for reconstruction model capacity, since SSMBA relies on a reconstruction function that approximates the underlying data manifold, we might expect a larger and more expressive model to generate higher quality examples. So we investigate these models of varying size. So distal Roberta with 82 million parameters, Roberta base with 125 million parameters, and Roberta large with 355 million parameters. For each reconstruction model, they again generate a set of 10 augmented datasets and train a set of 10 models on each augmented dataset. I'm just wondering how much time would it have taken for these to train, because if you have 10 augmented datasets and 10 models, you already have 100 results to look into. We average performance across models and datasets. Table 6 shows the SSMBA displays robustness to choice of reconstruction model, with all models conferring similar improvements to out-of-domain accuracy. Using the smaller distal Roberta model only degrades performance by a small margin. So you can see on the out-of-domain performance, base and large are uh, performing better than distal, but the difference is uh, about 5%. For the corruption amount, how sensitive is SSMBA to a particular amount of corruption applied? Empirically, tasks that were more sensitive to input noise like sentiment analysis require less corruption than those that were more robust like NLI. To analyze the effect of tuning the corruption amount, we generate 10 sets of augmented data with varying percentages of corruption, then train 10 models on each dataset, averaging performance across all 100 models. Figure 5 shows that for corruption percentages below 50%, our algorithm is relatively robust to the specific amount of corruption applied. Out of domain performance peaks at 45% corruption, decreasing thereafter as corruption increases. Very large amount of corruption tend to degrade performance, although surprisingly all augmented models still outperform non-augmented models even when 95% of tokens are corrupted. In experiments on the more input sensitive NLI task, large amount of noise degraded performance below baseline, because then you might have altered words which were deciding the label and stuff. So you can see how the performance drops as the corruption percentage increases, peaking around 45 to 50%. For the sample generation methods, next we investigate methods for generating the reconstructed examples. Top K sampling draws samples from the MLM distribution on the top K most probable tokens, leading to augmented data that explores higher probability regions of the manifold. They investigate top 1, top 5, top 10, top 20, and top 50 sampling. Unrestricted sampling draws samples from the full probability distribution of tokens. This method explores a larger area of underlying data distribution, but can often lead to augmented data in low probability regions. For each sample generation method, we generate 5 sets of augmented data and train 10 models of 50 once again. Out of domain accuracy is averaged across all models. Figure 6 shows that unrestricted sampling provides the greatest increase in out of domain accuracy, with top case sampling methods all performing similarly. This suggests that SSMBA works best when it is able to explode a manifold without any restriction. So with this, it might be able to wander into regions where it normally wouldn't usually, and get more robust, because it would then be able to catch more different types of examples. For the amount of augmentation, how does OOD accuracy change as we generate more sentences? To investigate, we generate 5 datasets, for each amount training 10 models and averaging out of domain accuracy across all 50 models. Figure 7 shows that increasing the amount of augmentation increases the amount by which SSMB improves out of domain accuracy, as well as decreasing the variance in the out-of-domain accuracy of training models. So when you increase the number of augmented sentences, uh, it improves the out-of-domain accuracy as well as decreasing the variance in the out-of-domain accuracy of the different models. So the different models are now much closer as compared to when it was when there was no augmentation or fairly less augmentation. For label generation, we investigate three methods to generate a label for a synthetic example. Label preservation preserves the original label. Since the manifold neighborhood of an example may cross a decision boundary, we also investigate using a supervised model trained on the original set of augmented data for hard labeling of a one hot class label and soft labeling of a class distribution. We train a CNN model to varying levels of convergence and validation accuracy, then label a set of 5 augmented data sets with each labeling method. When training with soft labels, we optimize the KL divergence between the output distribution and the soft label distribution. For each dataset, they again train 10 models and average performance across all models. Unsurprisingly, soft and hard labeling with a low accuracy model degrades performance. As our supervision classifier improves, so does the performance of models trained with soft and hard labeled data. Once we pass a certain accuracy threshold, models trained with soft labels begin outperforming all other models. This threshold varies depending on the difficulty of the dataset and task. In ANLI experiments, labeling augmented examples, even with a poor performing model, still improve downstream accuracy. So you can see soft labeling outperforms both hard labeling and preserving labels once you cross this threshold, and this threshold varies depending on the task. uh, right, so if you're not able to get what this is basically representing, then going back to the original diagram of the architecture, they had mentioned that they can use optional self-supervision to generate labels. So in case where the examples are prone to be misclassified after augmentation, they might do this. Alright, so for the conclusion, in this paper we introduce SSMBA, a method for generating synthetic data in settings where the underlying data manifold is difficult to characterize. In contrast to other data augmentation methods, SSMBA is applicable to any supervised task, requires no task-specific knowledge, and does not rely on dataset-specific fine-tuning. We demonstrate SSMBA's effectiveness on three NLP tasks spanning classification and sequence modeling, sentiment analysis, natural language inference, and machine translation. They achieve these gains. The analysis shows that SSMB is robust to the initial dataset size, reconstruction model size, and corruption amount, offering out-of-domain robustness improvements in most settings. Future work will explore applying SSMB to the target side manifold in structured prediction tasks as well as other natural language tasks and settings where data augmentation is difficult. They've also thanked their partners and the people who helped him out for the comments and discussions. So let's have a look at their data pre-processing. So all of this is you tokenize using a GPT-2 style tokenizer and byte pair encoding vocabulary provided by FairSec. The BP vocabulary consists of all of these things. Alright, input text and labels are then binarized for model training. Although all models share the same vocabulary, we randomly initialize each model's embeddings and train the entire model end to end. Also for machine translation, we follow this work and learn a 16,000 byte pair encoding on Opus and 32,000 byte pair encoding on D2RM. On IWS 7014, they learn a 10,000 byte pair encoding. We use a separate vocabulary for the source and target set. For model architecture and training, uh, all models are written and trained within the FairSec framework with a T4 GPUs. LSTM and CNN models were trained on a single GPU. Roberta were with 4, Transformer with 2. On average, when trained on augmented data, LSTM and CNN models took an hour to train. Roberta model took 12 hours to train to converge, and Transformer models took 24 hours to train to converge. Models trained on unaugmented data took roughly 20% of the time of models trained on augmented data to reach convergence. For each model, we investigate the model first, the model architecture, and then the training hyperparameters. Alright. They've just mentioned the structure and what hyperparameters worked for them for all the different models. So if you're going to re-implement this, this could be pretty helpful. And they've also mentioned the SSMBA hyperparameters. and the statistical testing. So for statistical testing on sentiment analysis, we use Wilcoxon ranked sum test. Specifically, we compare average of model performance on pair of training and test domain. For example, in a dataset with 3 domains, we have 3 in-domain and 6 out-of-domain pairs. Okay, so out-of-domain would be when you split a dataset into when you have a dataset with 3 domains, then you train on one and test on the other. So basically, choosing 2 out of 3, so 3C2. We calculate the average performance for each model on each pair, then compare the matched in-domain and out-of-domain pair. Since the number of samples we can compare depends on the total number of domains in the dataset, a larger number of dataset gives a better sense of statistical significance. For the statistical test on machine translation task, we use a paired bootstrap resampling approach. Since the test model works only on a single system output, we run the test on every pairing of seeds and test domains for the two comparison models. We report the significance level only if all tests result in a small enough probability. Alright, so it is mentioned uh, the hyperparameter uh, SSMBA hyperparameters were used to generate augmented data for each data set and domain. Hyperparameters were selected by in-domain validation performance. A star in the domain indicates that hyperparameters are the same for all domains in that dataset. Alright. So overall, this paper was pretty great. I feel it introduced me to this new technique SSMBA, and I plan to re-implement this myself using TensorFlow, just to hone my skills as well. So thank you guys for joining in. If you have any questions, just comment them down below. The PyTorch FairSec implementation is also present here if you wish to check that out or use that for your own work. So thank you guys for tuning in. Hope to see you again next time.